Good morning, good afternoon, and good evening. Welcome back to Chapter 10. We're talking about viruses now. Quite a topical subject, right? Let's talk first about what a virus is. First of all, a virus is a non-living infectious particle. Why are viruses non-living? Okay, to be alive, you've got to eat. If you eat, you make waste. To be alive, you must be able to reproduce on your own. And when I say on your own, I mean maybe not just you personally, but you and another member of your species should be able to make babies. There's a whole bunch more conditions that we say you have to be considered alive. And viruses don't do any of these things. Viruses do not eat. Viruses do not poop. They don't create waste. Viruses cannot reproduce on their own. They have to use the cellular machinery of a host to be able to reproduce. Non-living infectious particle. Next. Next is, if you imagine the size of one of your cells. If this is the size of one of your cells, then a bacterium is about this big, actually smaller. A bacterium is about that big, all right? And if that's the size of a bacterium, then a virus is about that big, okay? Your cell, bacterial cell, virus. Viruses are really, really tiny. They are non-living infectious particles. They're just a protein coat surrounding a protein coat surrounding nucleic acid. So let me pause for a minute. Let me explain this a little bit, and then we'll do some generalizations. When I say nucleic acid, I want you to imagine DNA, because for our purposes, that's good enough. You know that DNA is instructions. We know that DNA is what you use to make genes. Genes are a particular set of instructions. You put a bunch of genes together, and you make this thing called a chromosome. So viruses are essentially a tiny chromosome covered in a protein coat. How many genes might it be? It could be as little as 5 genes. It can be a lot more than that. It's usually a lot more than that. Not all viruses use specifically DNA as their genetic code. Some use RNA. There's a whole bunch of different varieties of viruses, whether you use double-stranded DNA or single-stranded DNA, double-stranded RNA, single-stranded RNA. There's a whole bunch of different classes of them. But for our purposes, we're just going to say DNA inside. So a protein coat that contains DNA. And that's all a virus is. There's no organelles in there. There's no cytoplasm in there. Nothing. DNA coat. That's it. The way viruses infect us is the first thing that happens is the virus attaches to the host cell. Here's my host cell. This is my virus. The virus attaches to the host cell. Once it attaches to the host cell, it injects its DNA. Now that the DNA is injected, this protein coat that was once carrying the viral DNA is useless. In this respect, a virus is a lot like a bullet. You've got the brass and the brass shell, and you've got the lead bullet to make a total bullet. The lead bullet is the thing that goes really fast into things. The brass is just the holder and the ejector. The protein coat would be the brass. The viral DNA, that's the bullet. Once the viral DNA has been injected into the host, the brass is useless. And it's done, and it can't be reloaded. They're single shot. Virus attaches to the host cell and injects its DNA. That viral DNA now will take over the host cell, and it will make the host cell make new viruses. So we have a bunch of different bits and pieces of the virus that have to be assembled. We have the DNA, we've got the head, we've got the neck here. They all have different names. We don't really care what those names are. But all these different pieces have to be constructed, and then once constructed, they have to be assembled into a proper virus. Once the cell has been exhausted, which means it can't make any more viral particles, the cell pops. One virus infected this host. That host made a half a dozen viruses and released them. That is the viral infection strategy. This is called the lytic cycle. It's called the lytic cycle because when the virus is done with the cell will lyse. Lyse means to pop. The lytic cycle. Every virus uses the lytic cycle. Every virus will take over a cell's machinery, make that cell make more viruses, and then kill the cell at the end. Some viruses also use the lysogenic cycle. We start off the same way. The virus attaches to the host cell and it injects its DNA. That viral DNA will insert itself into the host DNA. Note that there's now a new little section of viral DNA. And then it won't do anything. And then it just sits there. And then when this cell goes through the cell cycle and gets to the point to where it's ready to divide, it just divides. Part of the cell cycle is replicating its DNA. Well, there's a new little section of viral DNA in here, and so that's what it does. It replicates its own DNA plus that little piece of viral DNA, and now my one virus-infected cell splits in two and becomes two virus-infected cells. And then those cells will go on and live their life and do what they're supposed to do, and at some point they'll divide, and they'll continue on that same plan as though nothing were wrong. And then at some point in the future, and we're not always sure what the trigger is, but there's some trigger in the future that will cause all of that viral DNA to pop out of the host DNA. It exits the lysogenic cycle, and it enters the lytic cycle. The difference is, in this scenario, it was only one cell that was infected. In this scenario, that one cell becomes two, the two become four, and that could go on for a long time. So it's not just one cell that pops out and is infected and makes viruses. Now it may be a dozen or 100 or 1,000 cells that all suddenly enter the lytic cycle all at once. I only infected one cell, but because it just sat and hid and waited, it was patient. And it waited for that cell to reproduce a number of times. And after it did, now it's like, okay, now it's time. And then all of the cells enter the lytic cycle at the same time. And so it's not just one cell that ruptures releasing viruses, it's thousands of cells that rupture releasing viruses. Massive infection all at once. Remember, every virus uses the lytic cycle. Some viruses also use the lysogenic cycle, where they insert themselves and they'll hide. An example of a virus that uses the lysogenic cycle in humans is cold sore virus. Cold sore virus does that. It inserts itself into the host DNA and it just sits there. It's called cold sore because usually they erupt when someone is getting a cold, when someone's getting sick. We're not always sure, but it's always stress related. Some sort of a stressor causes the virus to say now is the time. And then all of the cells that have that viral DNA will pop out and they'll start making viral particles. And that's what the eruption is, and that's what the crust is. That crust is blood and pus, which contains viruses. If you have an active cold sore outbreak, don't kiss anybody. Where did you probably get that cold sore from? You probably got it from your mom. When your mom kissed you when you were a baby, when she had an active cold sore. So, if you have an active cold sore outbreak, don't kiss anybody. Don't kiss anybody anywhere because the cold sore virus is herpes simplex 1. It can become herpes simplex 2 if you kiss somebody where herpes simplex 2 is found, which is the groin. Where do new viruses come from? Have y'all had any experience with this? New viruses just showing up? Where do new viruses come from? They come from a number of different places. One place they come from is mutation, and that is that this process, if we go back and look at it again, this process right here of making and assembling the viruses is not very good. This process can be likened to a foreign invading army taking over a shovel factory and making them make swords. How good are they going to be at making swords? And the answer is probably not very good. Can they probably do it? Yeah, they could probably make some functional swords, but that's not what the equipment was made for. The equipment was made for making shovels, not for making swords. So accidents happen, errors happen. And that is that the DNA doesn't always get packaged right, the DNA doesn't always get read right, it doesn't always get copied right. There are errors. And when we have errors in DNA, we call that mutation. So viruses, because of the very nature of how they reproduce, by taking over cellular machinery, errors happen all the time. And these errors, because there are so many viruses that are made, some of them can be beneficial errors. And I know that an error doesn't sound like it could be beneficial, but sometimes you accidentally pick the right answer on a test, right? Sometimes you can make a mistake that's actually right. And that's what these mutations are. New viruses can show up also through contact between species. And I know we probably are all quite familiar with the coronavirus. The origin of coronavirus probably came from a bat, and then it went from a bat to a pangolin. If you don't know what a pangolin is, go look it up. And then from a pangolin to a human. Our best guess where the COVID-19, where the coronavirus that emerged in 2019, where COVID-19 came from was their so-called wet markets. Wet markets are open-air markets in usually Asian countries where there are live animals and butchered animals and all kinds of everything just on the street, up and down the street together. Animals from all over the world that never came in contact with one another, bringing all of their rare and unique and strange diseases together. And so what can happen, what can rarely happen, is a disease, a virus can hop from one animal to another, mutate inside that other, and then get passed on to another species, and sometimes that other species is humans. This is our best guess as to where the coronavirus probably came from. Probably came from a wet market in Wuhan, China, which has gone now so far as to ban wet markets. You can't do it anymore. And that should dramatically reduce the spread of stuff like this. And the last thing is viruses that are being spread from isolated populations. There are a number of populations out there, a number of human cultures out there that don't really have a whole lot of contact with the outside world. And as the outside world comes in and has contact with them, or some of them leave and come out, way more often we go and find them. Sometimes you can bring out rare diseases. An example would be like smallpox was brought to the U.S. Or to North America with the conquistadors. Oh gosh, there's just dozens of diseases. The plague was brought over. Contact between formerly isolated cultures. That's how we can, new viruses is where they can come from sometimes.